Yes.
You need to accept. You need to accept.
Yes.
No. No. It's him.
How about now? I see the echo. Yes. Can you mute?
I am muted, right?
And take your audio away. All right. Now.
Without now?
Yes.
Is it okay now?
Yes.
Okay, very good. Okay, so no, this is not working. Okay, I cannot move my pointer. Okay, so in our current paradigm of structural formation, we have these fluctuations measured by, say, a W map or Planck, and these temperature fluctuations, if they are adiabatic, then translate into fluctuations in the density field. And I think one of the results from Planck was actually that the other mode of producing fluctuations, isocurvature fluctuations, were essentially excluded. So we know that we have adiabatic fluctuations, and therefore these temperature fluctuations translate into density fluctuations, out of which through gravitational instabilities produces filaments, galaxies, clusters, and so on. So, you know, from linear scales to nonlinear scales, the CDM picture has been amazingly successful, both on scales of galaxies, all the way to filaments. But if you look carefully, independently of the sort of simulations that one does, they still have problems on scales which are not the scales of clusters or galaxies. On very large scales, like hundreds of megaparsecs, you have the cosmic web. and cosmic wave has not been detected in baryons. It has been detected through weak lensing in particular, but we don't see the baryons there. And in principle, most of the baryons are actually in the filaments. Likewise, on the highly nonlinear scales, like dwarf galaxies or scales of tens of kiloparsecs, we don't see the abundance of small halos that was predicted by theory. And so we have problems both on the weakly nonlinear scales, on the highly nonlinear scales, even though the intermediate regime is quite well sampled. So this is the aims of this project, is to actually test the lambda CDM paradigm on these two very large different scales. So on nonlinear scales, we're going to have a complete inventory of dark matter halos. And I'm going to argue that the surface brightness selection effects prevent us from actually getting the whole range of galaxies. So we have not a proper volume limited sample of galaxies, even in the local group. And so the question that we're going to answer is whether all dark matter halos host galaxies. And we're going to see this is related to the nature of dark matter and its power spectrum. And likewise, on the linear scales, we're going to understand the properties of the baryonic web. And again, in spite of having very different scales from hundreds of megaparsecs to dozens of kiloparsecs and different densities, they share one common property, which is to have very low surface brightness. So both these small subhalos and the cosmic web, they have surface brightness levels which are essentially undetectable from the ground or extremely difficult. And both we want to understand how this IGM feeds the dark matter halos on small scales, and there are many predictions depending on how you do dynamical simulations or the relative sampling effects. So science case number one is actually to test the abundance of these small halos, subhalos on galaxy scales. And Sloan has been instrumental in getting new satellites around the Milky Way. And you do this by actually subtracting, if we can, we don't see it, okay. By subtracting the foreground stars and getting the galaxies, some of them, 60 kiloparsecs away. So, satellites of the Milky Way, which were not known previously. Now, in spite of this success, the abundance of these galaxies around the Milky Way is orders of magnitude below what is predicted. And so the tension perhaps is so strong that you may say, perhaps we have to change the nature of the dark matter particle. If you have, say, self-interacting dark matter or warm dark matter, you're going to erase power on small scales and produce less subhalos. But I'm going to argue that perhaps too early. Perhaps the vanilla core dark matter scenario is fine because perhaps observations are wrong in SESA. They are biased. And let's have a look at the discovery rate of satellites around the Milky Way. You see, in the 80s, when we made these predictions, we knew something like a dozen satellites around the Milky Way, essentially through photographic plates on Schmidt telescopes. Then Sloan was instrumental in getting essentially twice the number of satellites. And now DECAM, and eventually DES, is just shooting up the number of satellites around the Milky Way. And so if you extrapolate the sensitivity of DECAM to the to further scales and the whole sky, you will probably get something like 300 satellites. And this is pretty close to what CDM is predicting. Now, the nature of these new galaxies detected around the Milky Way is very different from the classical picture that we have of galaxies. For instance, this is the Crater 2 galaxy. This is 120 kiloparsecs away, the fifth nearest galaxy around the Milky Way. And here I had to multiply its luminosity by 100 million times so you could see it. You see, it occupies something like twice the size of the moon on the full sky. But if it weren't for this loss of brightness, it would be shining like this. Now, you see the surface brightness is something like 31 µm per second at the effective radius. And so this is extremely faint in surface brightness. In fact, this galaxy is in strong tension with the CDM. You're not supposed to produce galaxies this way, but this is not the subject of today's talk. But the nature of these galaxies is really particularly interesting in this context. Now, again, these denizens of the local universe will go from something like 10,000 times to 100 million times fainter than the Milky Way. And again, we detect them because we can resolve into stars. Now, if these galaxies were not, say, 150 kiloparsecs, but at 20 or 100 megaparsecs, we will not be able to detect them because they will be just small patches under the sky background. So, if you look back at archives like at Subaru and look at the Coma cluster, well, you find this population of ultra-diffuse galaxies, which is actually more abundant than the population of normal quote-unquote galaxies. In fact, if we have something like 300 galaxies in the normal catalogs, well, all of a sudden, you have something like 1,000 new galaxies in this cluster. So we don't know properly even the best studied cluster in the universe. Now, these galaxies, again, are very different from the normal picture that you make of galaxies. You see, if all galaxies were the same distance, you will have the giant galaxies like Sombrero, M31, and you will have small galaxies, dwarf galaxies like NGC 205 or Fornax. As you somehow we associate dwarf galaxies with small sizes and small luminosities. But these new galaxies, ultra-diffuse galaxies, are as large galaxies and as faint as dwarf galaxies. And again, this is a surface brightness selection effect. We'll not be able to detect these galaxies because it's extremely difficult. The contrast with sky background is too small. So this is the deepest exposure ever done. This is done by an amateur astronomer on the intracluster. And most of the galaxies that he's detecting are not in our catalogs. See, in white, those are the known ones, but the red ones are just new galaxies were not detected by our professional instruments. So we're missing a huge number of galaxies because we're not able, and this is again, amateur astronomers. I mean, they don't construct the sky properly. They have problems of PSF and so on. So we don't know how many galaxies there are, even in the local universe. And these galaxies are extremely interesting because the mass to light ratios speed up to something like 1,000, just like in cluster scales. So again, those are the best labs that you may have for dark matter studies, again, on small scales and galaxy clusters. Now, if you look at luminosity versus, say, half light radius, you have the pluses, which are global clusters and so on. You have the blue ones, which are the local group galaxies, and then use these new galaxies in red triangles. They span a range between something like 25 to 30 miles per square second surface brightness. And there's no reason why the lower right triangle is not populated with lots of galaxies, except that we cannot detect them because they will be at something like 34. And that's essentially undetectable from the ground or even from space. So again, most of this is done with star counts because you can resolve into stars. But if those galaxies were further away, they would be just undetectable. So again, it is a picture of the loss of brightness. We're used to see the sky background as black and galaxies like island universes standing up from this dark background. This is completely wrong. This is a surface brightness selection effect. The actual M31 galaxy that we did at CFHT didn't move to the right place. Anyway, you can see that the actual disk of M31 is huge in comparison to what you see in normal pictures. You see streams, you see dwarf galaxies being disrupted by tidal effects. You see the S-shape isophotes around M33, again, a tidal interaction with M31. So the actual picture of M31 will actually be like this, not like the posters that we've got in our offices. Likewise, if you look at ellipticals, well, some will say they are red, dead, and boring because you look at an HST picture and it's not very interesting. But if you go deep in surface brightness, then you get all the shells and streams around this galaxy. Again, we're witnessing galaxy formation. All these galaxies are falling into the potential well of this elliptical galaxy and transforming subpopulations and the galaxy's properties in general. So, but again, this requires going to low surface brightness, not fluxes, and we'll see the difference again in a minute. So what we actually need to test the CDM paradigm of accretion and merging is to reach something like 34 magnitudes per square second. And here you have the state-of-the-art simulations, and you see that you reach something like 29.5, which is the state-of-the-art currently from the ground or even from space, and you're missing most of the activity going on. And you really need to go something like 34, and that's extremely challenging. And likewise for dwarf galaxies, you expect them to have halos, but again, below something like 31 or 32. Okay, so second driving science case is the cosmic web. You can look at the web at say oxygen 6 line at 1032 angstroms, and that's interesting, but it is a collision ionized line. Therefore, the intensity will go like the square of the density. You will see the very dense clumps but you will not look at the cosmic filaments on very large scales. For that, predictions from simulations say that Lyman-alpha will be 3 orders of magnitude stronger than any other metallic line. So it makes sense to look for Lyman-alpha. And the idea here is to look at Lyman-alpha at low redshift. And there are 3 reasons for that. First, the stronger filaments that are predicted at redshift below 1. Second, you minimize cosmological dimming. Remember that surface brightness to first order is independent of distance, right? The flux decreases like distance squared, but the area increases like area distance squared. Therefore, to first order, surface brightness is independent of distance on light flux. But of course, on larger scales, you have the expansion of the universe, and that produces a dimming like 1 + z⁴ power. And then the third good news is that now we have efficient UV detectors, so we can look at Lyman-alpha at low redshifts. So this has been, of course, attempted from the ground, and the state of the art is probably MUSE, reaching something like 10 to the -19 in these units. And they found that a redshift above 3 or so, essentially all galaxies are surrounded by Lyman-alpha halos. But again, on scales, of a few tenths of arcseconds at redshift 3, and those are a few dozens of kiloparsecs. What we want to extend this to, say, 2 orders of magnitude below, and actually detect the connection between the halos and the cosmic web. So again, this is one of the predictions from the many simulations that we've got from Joris, and he shows that below redshift 1, the surface brightness of these galaxies, of these filaments, sorry, will be much stronger, but at least 1 to 2 orders magnitude above what is done at redshift 3 or 4. So it makes sense to look again at the cosmic web at low redshifts. So I'm going to argue that we're not detecting this because galaxies are just like icebergs. And this is an idea from Michael Disney back in the 70s, saying that what you see above the sky background has nothing to do with what lies below. And this is just like current paradigm today. We have 5% of baryons, and everything else is just below our way of detecting it. So surface brightness, again, is very different from fluxes. I will come back to that in a minute. But this is the classical picture that you get of the sky. Galaxies, a few stars. But this is because you're limiting yourself to something like 21.5. If you go down in surface brightness, then you realize that no galaxies actually have no edges. They trail off in intergalactic space. And eventually, by reaching something like 29.5, you see that the sky is full of photons. Interesting. Now, this is old technology. This is a Schmidt telescope, but using state-of-the-art detectors and baffling and so on. So Prismy has been doing a wonderful job. But again, this is limited by systematics. The first is sky variability. When you look at the sky, it is changing both on angular scales and temporal scales. And the way of monitoring this is extremely difficult. Second, you have stray light. And here we're dark enough, we still have some light over there that will reach the detector and will just boost the surface brightness. So preventing stray light is very challenging. Then you have flat fielding. You don't know whether at this scale you have under-subtracted, and at that area that you have over-subtracted. So the accuracy with which you measure the flat fielding is extremely important. And then, of course, you have all the black circles. You have to remove the stars because they will have extended PSF wings that will also boost your surface brightness. Now, you have to, so you think about, okay, let's detect these missing galaxies, let's detect the cosmic web. You have just to design something that will just limit all the systematics. And so this is the key idea. We are thinking about fluxes usually because we think in terms of counting stars or detecting galaxies further away, which are extremely compact. And for that, we want to just, for a given exposure time, for a given magnitude, you want to maximize the collecting area. That's fine. But this drives, ELT-like telescopes. But what will the physically relevant quantity here is surface brightness, flux per unit area. And for that, it's very different because then what matters is actually the F ratio, the focal length divided by diameter squared. So if you have something like F of D of 3, with respect to, say, Hubble, F of T of 20, you will be 2 orders of magnitude more efficient in terms of detection for a given exposure time for a given pixel size. So the key thing here is to have fast optics as opposed to slow optics. And this is one of the drivers for this new instrument. So we need something like a large field of view because we're going to go to space, obviously to minimize the foreground. We want a focal ratio as small as possible. We want no obscuration because we're going to lose photons for one thing. And second, of course, if you have obscuration, you will have extended PSF wings. And in fact, you actually want very compact PSF. You want something like 1 arcsec per pixel. It would be nice to have higher, perhaps, to reduce confusion noise, which is one of the issues. But 1 is fine enough. From the manufacturing point of view, the key quantity here is the roughness of the surfaces of the mirrors. And we'll see that in a minute why it is important to reach something like 0.75 RMS nanometers. Then the key thing is flat fielding, as I said. And usually, in astronomy, we get 1% accuracy in flat fielding. If you make a very, very strong effort to get something at 0.1%, well, we need something like 2×10⁻³ in order to reach the surface line. And the only way to do this is through time delay integration. You're going to clock your CCD at the same speed as which the field of view is going through your field of view detector. And this is what Sloan was doing. This is what Hipparcos, this is what Gaia has been doing. But somehow it is not getting enough into the ground telescopes. But that's the only way to get the accuracy in the flat fielding that we need. It means that, again, for an optical point of view, the distortion in one direction must be minimal, but in the other one, you're quite free. And we want to do the whole sky because this is going to be a unique survey. So why am I so obsessed about PSFs? Well, remember, if you have a clear aperture, then you are essentially the AV function. If you have an obscuration and then some struts supporting the secondary mirror, what you get, again, is some very extended wings and then very anisotropic PSF. I mean, this is the case for Rubin, and don't get me wrong, Rubin is a wonderful instrument, and it will do excellent science. But in terms of loss of brightness, you will have to deconvolve with this very anisotropic PSF, and this is going to be quite challenging. And likewise, Euclid, again, Euclid is a fantastic instrument, but the wings of the PSF on scales of dozens of arcseconds, that's the interesting scale for us, are going to be very, very challenging. So why this is a problem? Well, let's have a look at, again, this elliptic galaxy observed at CFHT, and then what an amateur astronomer did, at CFHT in less than an hour, you get these shells. He took 21 hours. But look at the PSF. The PSF of the amateur is far more compact than the one we get at CFHT. And the reason is that, at the prime focus corrector, you have so much internal scattering that actually scatters photons out of the optical axis into this extended PSF. So if you want to do the photometry of these shells, I'd rather use the PSF from the amateur than the one from CFHT. And again, this is something that we're not used to. Usually we want to characterize the PSF on scales of something like 5 to 10 arcseconds, where we're dominated by essentially the core, the diffraction pattern. But because we want to see the extended features, we need to measure the PSF on scales of dozens of arcseconds, even thousands of arcseconds. And then you have two effects. One is the internal scattering of the lenses, as I've shown. And then as on large scale, you have the scattering by the molecules of the atmosphere. I mean, the sky is blue through Rayleigh scattering, but it is also blue at night. And this scattering is also producing this effect. And therefore, you don't have the AV function going down like crazy. You get these extended PSF wings on scales of thousands of arcseconds. And so obviously, from the ground, this is going to be next to impossible. We need to go into space. Now, there is another issue here, a bit subtle. You cannot use lenses. And one reason is the one I showed before. You have scattering produced by the internal reflections in the lenses. And the second is that you will have Cherenkov. Cherenkov's particles that will go faster than light in your lenses, and they will produce these flashes into your detector. Usually, if you're detecting point sources, you don't care about this. But when you're looking at very loss of brightness, these flashes will produce an additional foreground, and that will be extremely difficult to detect. And this is one example, not of Cherenkov, but of internal ghost images on ACS. And this is an ultra-diffuse galaxy that we are detecting. This is fainter than the ghosts produced by the lenses. So no lenses. So when we proposed that back in 2009, the optical engineers said, well, you cannot use a fast optics without lenses and a wide field of view. but I don't take no for an answer. And so we made a survey of all possible optical configurations for fast and wide field off-axis optics. And I can spend hours telling you about the merits of each configuration, but to keep a long story short, this is the current configuration. We no longer have parabolic shaped mirrors, we have free-form mirrors. So we increase the number of degrees of freedom on the shapes of the surfaces. And in this way, you can actually get f/3, an aperture something like 400 millimeters, large field of view, and something which is quite easy to manufacture. The breakthrough was that there are two satellites, one MATS from Sweden and another one from France, Microcam, which are actually using these new shapes for the mirrors. We also explore a solution with curved focal planes, but this is even more challenging. Okay, so let me go through. Okay, this is one of the reasons why it is easy to manufacture. The deviations from the base sphere are quite small, and you can actually do this with 3D printing, essentially. Now, another issue that we forget, and this is a discovery for me, because coming from theory, all of a sudden getting my hands dirty into instrumentation was a discovery. But the thing is, again, at the core, when you look at the inner arcsec around the optic galaxies, you are essentially diffraction limited. The AV figure will go will dominate the PSF at the red wavelengths. But if you go to the UV, what actually matters is how rough the surfaces are. And if you go into the wings, then it is not only the roughness of the surfaces, but also the dust contamination. If you have dust particles on the surface of your mirror, it will scatter away, and you will not have a compact PSF. So having an ultra clean mirror is one of the challenges actually of this mission. So in terms of filters, well, we have designed these 4 filters, 3 to be long ones of the Balmer break, and 1 essentially wider than the U-band to characterize the star populations, the gravities, the effective temperatures, everything that is below the Balmer break is sensitive to, and then 2 filters around 200 nanometers to detect the cosmic web. So if you image the same area of the sky in these broad and narrow band filters, and you make the subtraction one of the other, you can get the emission line only pixels, and that will be the cosmic web. So that's the configuration of the field of view, something like 4.4 times 1.6 degrees on the sky, and you're just scanning the sky, and you're plotting your CCD at the same rate. So this is very efficient. You're reading all the pixels all the time. There are no moving parts, and the cooling is passive. So this can go actually forever. And so each of the CCDs has quantum efficiency, which is optimized for that particular filter. So it's difficult to imagine something more efficient than this. On terms of straight light, the baffling is one of the key issues. So we made very careful simulations how much straight light is accepted. And here we're working with the CSL in Liège, Belgium, who actually designed the baffle for Coho and Chaos. So everything is pretty standard and has a strong heritage. The thermal subsystem is fine, the platform is fine, and the only thing which is truly new is having the baffle and this new optical design with freeform mirrors. But otherwise, everything is pretty standard and actually pretty cheap. Now, one of the nice things is that if you want to survey the whole sky, it makes sense to have what we call a sun-synchronous orbit, essentially a polar orbit, that will take advantage of the fact that the Earth is slightly flattened, and therefore the orbit will precess. So you can choose the orbit and the inclination of the orbit such that the precession rate will be few 160 degrees per year, 195 per year. And so you see one orbit will go like that, and second orbit will be slightly offset due to precession, and eventually after 6 months you cover the whole sky. So this is very nice because then you're pointing away from Earth, so you minimize Earth shine, close to 0. You have the one of the faces looking towards Earth, so you can download the data. And one of the inconveniences here is that one of the faces will be facing the sun all the time, and they will induce thermal gradients. And that's something that we looked in some detail. So this is what we get as sky coverage after 6 months. The ecliptic poles obviously are oversampled, actually one measure every 90 minutes, which is the period. And then, of course, you have to take into account the dark blue bands. That's when the moon is closer to 35 degrees from the field of view, in which case you cannot observe because you get too much stray light. And then we have now added the South Atlantic anomaly. When you're crossing essentially above Argentina, you have to stop observing because, again, of these disturbances from the magnetic field. But essentially, you get 1 point every 90 minutes at the ecliptic poles, I mean, a much wide area. And then at the ecliptic, you get the same for something like 2 days, and then you move out along the year. So one of the challenges is that, of course, you're reading all the pixels all the time. You're not pointing and staring at an object. You're just letting the sky drift through. So you're reading all the pixels all the time. It's 100% efficient. The problem is that you produce something like 4.4 terabytes per day, and you have to download that. Now, the good news is that there are still few photons per pixel, and you can compress that lossless in a very efficient way. And so we expect something like less than 2 terabytes per day, which is something that the antennas on the platforms can do. Now, the nice thing also about the sun synchronous orbit is that you get 2 passages per day anywhere on Earth. And so we have a set of antennas that actually can collect more than twice. If you get high latitudes, both in northern or southern hemisphere, you can get something like 4 to 6 passages per day, and therefore download all the data without any issues. Okay, so those are the thermal issues. So you see the sun synchronous orbit, and one of the faces facing the sun by design. And so that induces thermal gradients, which are pretty strong, and peak to valley, something like 0.1 degrees. But given the structure of the optomechanics around the telescope, that's perfectly fine, even though the depth of the field will be very small due to the fast optics. So we have been discussing with 2 different industrial partners, and to just make sure that we have the proper platform, proper proa, proper antennas to download the data, and the total budget, including launch, will be something like 153 million, including 2 years of operations. So with this, we set up a pipeline to look at the actual performances of the instrument, and this is what M31, the actual M31, not the poster child picture that you have, would look like at 150 megaparsecs after 1 megaseconds or 10 megaseconds exposure. And you see that by even after 6 months, you get something like 32, and after 10 megaseconds, you get 34, which is actually what it was designed for. And this is the, as I said, M31 if looked at 150 megaparsecs as opposed to 770 gigaparsecs. Likewise for the cosmic web, well, these are the pixels which will have an equivalent width of less than 200 angstroms grace frame, and so you see the galaxies. But if you look at the essentially infinite equivalent width, then you get the cosmic web. Okay, this is not surprising. Again, we have designed the mission for this. So we know we can actually follow the specs we wanted. We can do the one-dimensional power spectrum of the cosmic web. We can do also the two-dimensional power spectrum. So I can give you a talk on the beautiful data that we can get and cosmological information that we can get from the cosmic web. We can also do intensity mapping through broadband, and this is something we are doing very detailed calculations now. We can combine, say, the 6 filters from MESSIER with the 20 filters from SphereX, and then do the tomography of the stochastic background. So this was done recently by Scott using the Castor. This is a Canadian mission I will talk later, using 3 filters. And even with 3 filters, we can get very interesting results on the tomography of the stochastic background. Now, the beauty of this is that when we designed this instrument, we thought about these 2 key issues in lambda CDM, but then we realized that these full sky maps actually are useful for a wide range of scientific topics. And this goes from the solar system, the zodiacal light, all the way to cosmology, like the EBL. And this is something that we didn't design the instrument for, but it comes as a free byproduct. So I can actually spend hours for each science working group, but let me just flash a few ideas. So because we're looking always 90 degrees away from the sun, we're getting a measure of the zodiacal light every 90 minutes. And now again, I'm discovering this issue myself, but both comets and asteroids, they leave long trails in the interplanetary medium, and this was detected by IRAS, but has not been detected in the UV or in the optical. So again, this is new science that our colleagues in the solar system are interested. We can also do, because we have this very compact PSF, we can subtract it and try to measure exozodiacal lights or debris disks on scales much larger than the ones brought, say, by ALMA. So on scales of something like 100 astronomical units, you can actually get something like 50 of these disks from this survey. Stars are not points, not even point-like. They are extended emission because they lose mass. And when they lose mass, they produce these shells, again, on scales of 20 arc minutes. This is not small, and detected from all the way from the infrared to the UV. And again, this is extremely interesting because this is the material that is enriching the interstellar medium from the new generations of stars. So how many of these shells can be detected? Well, thousands, if we see abundance of these AGB or RGB stars. One example, of course, is Myra. With Galax, you see the bow shock of Myra against the interstellar medium and a tail that extends something like 3 degrees on the sky. So again, and Galax was not designed for loss of brightness. So how many of these features are going to detect? We don't know. Again, this new science is enabled by these maps. Because we have such a wide range in wavelength, from 200 to essentially 900 nanometers, we have a huge leverage on the magnitudes of the lower main sequence and the magnitude of the red giant branch. And because of this extreme sensitivity, we can actually measure the photometric metallicities of essentially all the Gaia stars. Again, photometric, right? Not spectroscopic, but again, you can do plenty of things. And for the surface brightness of these galaxies, you can also get a handle on their subpopulations. On the ISM, well, this is the classical picture of the Pleiades, and I hope that by now you realize this is wrong, because you see the sky is dark and Olbers is wrong. The sky is full of light, and if you go deep enough, then you see something like this. You still see the gas around the OB stars in the Pleiades, and you see all the Cirri. Those are those grains in the star space, which have the property of scattering us photons into our line of sight. So this is going to be the major foreground that we have to subtract, in addition to the zodiacal light. But the physics of these grains is extremely interesting because they are heated, and you can see the infrared emission, but usually the optical depth here is so small that you only see the scattering, you don't see the thermal emission. But if you look at the angular power spectrum of the emission from the Cirri, it is not even Kolmogorov. So it is amazingly a power law on something few orders of magnitude, but we don't really understand much more. So there's lots of things to be done with the same instrument. Here we have to combine Planck all the way to CFHT to get things. In clusters, again, we have to remember that when galaxies fall or interact within the potential well of a cluster, the gas, the stars, and the dark matter will be stripped, and therefore the evolution of these galaxy populations in the cluster will change. And you need something like 32 magnitudes per farad to actually see the remnants of these interactions within the potential well. So if we go deep enough, as we saw in the Virgo cluster image before, how this is going to produce changes in the galaxy evolution itself is, again, an open science case. Another thing that I'm very interested is baryonic acoustic oscillations. And usually, again, this is done with red elliptical galaxies. And the bias parameter of this one is probably much higher than, say, starburst galaxies. And that's why MESSIER will get something like 3 million galaxies selected only in Lyman-alpha. And therefore, the biases and the bias parameter of these emitters will be different. And so, the actual shape of the oscillation will depend on the tracer. And then here you have something to compare with the normal or the surveys that you have at redshift 0.7. You can also do time domain naturally, because you're scanning the whole sky. You're oversampling the ecliptic pulse, but we will get whatever supernova that we can get. And one thing that I'm interested in is the rest frame UV line curves of type 1a supernovae. And the reason, of course, is that if we want to measure the expansion rate, you are comparing rest frame UV, observing the optical from the ground, and therefore you have to have something to compare with. And optical light curves are not the ones which can produce biases with respect to the rest frame UV. So here we'll have rest frame UV light curves in the low redshift universe to compare with the ones at the high redshift, again to mitigate biases. Yes, so you also have another issue, which is because I started late, remember? Another thing is orphan supernovae or orphan gamma ray bursts. Oftentimes you do identify these explosions far away from the host galaxy. And if you just look at the velocities, they make no sense. And actually, if you go deep enough, you can actually see that you have a loss of a brightness galaxy underneath the supernovae or the kilonovae. So we have produced synthetic light curves for kilonovae using the MESSIER filters. And again, I can talk about this for a long time. You can also do the perturbations in the Einstein rings, because again, surface brightness is conserved during gravitational lensing, and so by going lower in surface brightness, you can have access to the gaps produced by the subhalos in the lens galaxy. Let me finish with the EBL, the cosmological background. Remember, this is the integral of the luminosity density over all redshift. It has been detected in the infrared, but not in the optical or the UV. And if you are following the subject, you have New Horizons. Remember this satellite that went through Pluto? Well, it is so far away that the zodiacal light is very low. And they have a measure of the background, which is much higher than anything predicted by the models. So if this is confirmed, again, it means there's something wrong with our models, and what is the actual properties of the background is often an issue. And it is not only the monopole that is interesting, it's actually looking at the fluctuations of this surface brightness cosmological background. So we have set up a huge team because there are so many people interested. So we have a scientific advisory board, which is essentially respects almost gender parity, and we have a number of national points of contact. Sadly, no one is really interested in Italy so far, but I hope this will change. So there is no NPOC in Italy, but I hope you will join us. And so we are something like 180 scientists from Australia to Canada, from Argentina to North Korea. Of course, most of us in Europe. Now, we have, of course, we're in competition with a number of other projects. One is Jian-10. This will be a Schmidt-like telescope on the Chinese space station. Again, large field of view with spectroscopic capabilities, sort of Chinese HSD, but slightly sensitive to surface brightness. You have Ultrasat. This is an Israeli satellite looking at the 200 nanometer band, looking for the counterparts of gravitational wave events or kilonovae and so on, and this will be launched in 2025. You have a small 12U or 9U CubeSat from Australia. We have UVEX. UVEX is a JPL or Caltech-led mission. Actually, they are looking at phase A at the moment, and NASA will decide within a year or so. And these are sort of super galaxies, more sensitive, and with capabilities of pointing a bit like Ultrasat. We have the Russian WSO, which has been delayed for many years, but they are now close to completion. We have Arrakis, which is a Spanish-led mission, which is a small version of MESSIER, I would say. And then you have Castor, a Canadian-led mission, which also has spectroscopic capabilities. But none of these are actually optimized for loss of brightness. So we have no competition. And in fact, if we compare with the current and the planned facilities, you see in this plot of the limiting surface brightness. And again, remember, we're not talking about fluxes. Fluxes are independent of the scale at which we're measuring them. Surface brightness depends on the angular scale. Okay, so the standard these days is try to measure things on scales of 10 arcseconds, 3 sigma. In which case, if we compare all these missions, you see that HST reached something like 32.5 on the narrow field of view of the ultra deep field. Euclid deep will reach something like 31 on the 2 deep fields, and then Rubin after 10 years will probably reach something like 31. But MESSIER is 2 orders of magnitude fainter and over the whole sky. So we essentially, there's no other, but it is not surprising we have been designing the mission for that. And likewise, we will be using the same instrument to cover the range from 200 nanometers to 900 nanometers with the same instrument, the same systematics. And that's really, really important for everything that we've been discussing. Another issue that I've been very sensitive to is what is the carbon footprint of this project. And it's very difficult to compute, depending on whether you compute that on the mass that we're launching or the cost of the whole thing. But something between 6,000, which is huge, but still is the smallest decile of the 45 missions that have been analyzed in this recent paper. So it's not perfect, but it's part of our scientific footprint. So the calendar has been is to be called for fast missions, and also we were selected in the first round, so we went to phase 2. We sent the final proposal in July, and in November the final selection is to be announced, and then if everything goes well, we will start in January 23 for launch in 2029 or 23. Now, last week, sadly, ESA selected Arrakis, and I think this is a huge mistake, and I can tell you why offline. But we're back to square one. It means that we have to convince ESA that in spite of having selected this mission, MESSIER surveyor still makes sense, because it will just cover a much wider range of science cases, and it will cover a much larger community. And if not, the Koreans are interested, NASA's interested. I am a scientist. I don't care who the PI is. I want to do science with those maps. So MESSIER, again, is not incremental science. It's something orthogonal to what you have been thinking so far. It has been designed to have a complete inventory of galaxies. So no galaxy will be left unobserved, well beyond the local group. We'll be detecting the cosmic web in baryonic Lyman-alpha emission, and then you can do follow-up studies in other lines, but you know where to look at. And you have a wide variety of science cases going from the geological light to the cosmological background. And again, because you're accessing 2 orders of magnitude below anything else, this will be a unique discovery machine. It will be the first time that we'll have a whole sky survey from the UV to the optical with the same systematics. And again, because perhaps I come from this theoretical background, I made sure that implementation has the lowest risk. So this one single observing mode, TDI, drip scanning, there are no moving parts, and it is passive cooling. So if you're interested, I very much encourage you to join us in this adventure. Even though we had a setback last week, we will continue. Thank you.